Welcome to IKOI. I am Giovanni Fauro and I look forward to meeting you in Berlin to introduce our latest technology. This will be a great opportunity to learn why we are busy creating the most efficient way to destroy precious metal bars.
So, ladies and gentlemen, this is IKOI, and this is here, of course, Enrico, traveling all the way from his beautiful country to Berlin to present today the optimizing the refining processes. So, in your house, at home, if you at any time want to optimize your refining process, this is the man to talk to later. So, thanks, and give him a big hand for. The floor is yours.
Thank you. Thank you. Thank you very much for the introduction and also for the opportunity to be here to talk to you a little bit about our company and most of everything about the latest development that we are bringing forward in terms of refining techniques and technologies. During this presentation, I will touch few topics. The first one is an overview about our company, very briefly, to give you an idea about who we are. And then we will go through a very quick review of the main existing refining techniques and technology and processes. We will focus on two of them, which are very, very common in the industry, from small, medium, and big refiners, precious metal refiners, and then we will bring what we think and we know that is an innovation to this kind of processes, as well as other precious metal refining processes. The last part will be a comparative test that we have done between the old technology and traditional technology and the innovation that we are bringing and we are presenting with this speech. Let me give you a few words about IKOI as a company. We are an Italian company. We are based in the northeast part of Italy, not far from Venice. And the company was founded in 2010 with one specific mission and vision, which was bringing innovation to the precious metal industry, broadly speaking. And the first thing that we did when the company was established was to look into the casting process. Because of our heritage, it was very easy for us to start from that part. And we developed at that time the patented technology of the tunnel furnace for bar casting, which is named flameless tunnel, which is now the benchmark and the standard for the industry. Immediately after, we put our attention to the refining process and we introduced another technology that is very disruptive. It's called ALS, or acidless separation. It's a vacuum distillation technology. It's a kind of technology that I know other companies at the technical forum has introduced from the point of view of the user. And obviously we have the point of view of the manufacturer of this kind of technology. And then we switch back our attention after a few years to the casting again, developing a series of automation in the casting industry to be able to effectively produce product from the smallest bar to the biggest one in a fully automated way. Now we are here today with the focus that is again towards the refining process, introducing the latest development that we did. With this slide, I just want to give a framework to where this presentation sits and where, to have an understanding where this presentation sits. On one side of the slide, you will see just a summary of all the activities that are very common in a precious metal refinery and minting. And we have things like melting, casting, rolling, stamping, everything that you know very well. And that gives an idea about how sophisticated and how complex these kind of organizations are, and how most of the time these companies are vertically integrated. They do a range of activities that is very, very different in terms of skill set, in terms also of technology. Even if we take a subset of these kind of activities and we focus on the refining side only, we still have a range of technologies and processes, our ALS, but the aquarija process, the electrolysis process, hydrochlorination, inquartation, and so on. And the list here is not even exhaustive. So this is all part of the toolbox of the refineries, which are facing every day a challenging job in all, in every single one of their activities. Specifically, within this framework of refining processes, with this presentation, I will be talking only about two processes, the aqua regia process and the electrolysis process, and I will introduce an innovative technology that will have an impact on this traditional technology. Couple of words about the aqua regia process. I'm quite sure that most of you are familiar with this refining technique, which is basically a chemical dissolution technique. The aqua regia is a mixture of nitric acid and hydrochloric acid, and it is used to basically dissolve gold in a two-stage way. The nitric acid is promoting oxidation of gold and creating in this way ions. These ions are then stabilized by the hydrochloric acid to create chloro complexes. It's a very well-known process, very well established, and there are many, many companies that are using this kind of process. The other refining process that I want to touch on is, again, very common in many refineries, and is the electrolytic refining. Slightly different from the aqua regia is an electrochemical process in which we have an electrolytic cell and we perform dissolution and deposition in two different parts of the cell. You have to think about the cell as a sort of a battery in reverse, in which we have an anode and a cathode and an electrolyte, and we pass current through this system. What happens at the anode is that we have a dissolution of the gold that goes into solution. The solution is, again, a chloro complex with gold in it. And on the cathode side, we have the deposition of the pure metal that has to be refined. The pure metal refined at the cathode grows slowly, and after a specific period, it is harvested as a pure metal with high purity, 4,9 or even more. So these are two refining techniques that are somehow different in nature, but they have some similarities in the basic principles. And one of the things that we looked at is going to the key parameters that are governing both these processes. And we realized that one of the most important parameters that is governing the process is the surface area of the feedstock that we have to treat. To give you a simple explanation, the interface between the metal, the feedstock that we have to refine, and the liquid where we have our reagents is where the reaction happens. So if we maximize the surface available for the reaction, that should have, and as we will see, will have a positive impact on the refining itself, both on reaction speed and also on effectiveness of the refining process. Based on this principle, we did one thing. We developed a technology, which is a machine, that can create a very, very high surface feedstock. And we call this, and the process that is related to this, high surface refining. In simple terms, we are taking precious metal alloys, impure metals, we are transforming physically, mechanically these alloys into a high surface feedstock, and then we are applying this chemical and electrochemical process to this new type of feedstock. This is something that is quite known, is well known, that the surface obviously has an influence on the refining and on the performance, but I think that we move to a step forward. We create something that is quite easy to produce and has an effective surface that is an order of magnitude bigger compared to the other feedstock type that we see normally in the industry. These are just some pictures. It helps me to give you an idea. What we are creating with this is a thin layer of material, a thin strip, you can call it. But it's not only the fact that it's a thin strip that is very important, it's also the fact that the surface is very rough as a consequence of the process, with crest and trough, where the actual surface is maximized and the reaction can happen in all these rough surface. So the real available surface of the feedstock is as I said, an order of magnitude compared to the geometrical surface that you can infer from the shape of the feedstock itself. This has a positive consequence in terms of two parameters which we tested. One is the reaction speed, which translated to a shorter refining time, which is a key parameter for all refiners. And the other one is the effectiveness of the reaction itself. When I say effectiveness, I mean the capacity to recover completely the gold that is in an alloy, even when the alloy is a bit difficult to treat, when the silver content is high and there are some limitations to the traditional processes. We did some testing on that based after we developed the technology, and we separated two tests in two families. The first one is to understand how much this type of feedstock has an impact on the reaction speed. And what we did, we test in different batches 100 grams of pure gold, 49 gold, in two shapes, what we call the high surface refining feedstock and the traditional flakes that are usually used for aqua regia, which are produced by pouring liquid metal into a water tank or similar ways. What we noticed is that the reaction speed, specifically the dissolution speed with the high surface refining feedstock is 6 to 8 times faster than the other feedstock. And this is already a very positive indication about how much you can speed up your refining time if you are using this kind of feedstock. But more importantly and more interesting is the second set of tests that we have done, which is about testing what are the boundaries and the limit of refining processes that we can have if we apply this feedstock. What we have done is repeat similarly the test, but this time not using pure gold, but an alloy that is 85% gold and 15% silver. Now, this type of alloy is known to be on the boundary of between the very easy alloy to be refined in aqua regia and the not so easy alloy to be refined. The reason being that this amount of silver creates silver chlorides when it is immersed in aqua regia, and silver chlorides they do not go in solution. They tend to stick on the surface of the metal, and they create a coating, not the type of coating that we've been discussing and you've been discussing a lot, but a barrier for the reaction to continue to dissolve the gold. The end result is that when you treat this type of alloy in a traditional way, sometimes you are not able to recover all the gold that is in the initial alloy. There are some tricks, there are some ways to cope with that, but there is a fundamental limitation, which starts at 15% of silver, and if you have 20% of silver, is even more difficult because the amount of chloride that will coat the material is getting bigger and bigger. So we've tested this again with the two feedstock, the high surface refining feedstock on one side and the traditional flakes on the other side. The results that we get are extremely interesting because we saw that we can recover 99.99% of gold using the high surface refining feedstock, so basically 100% of all the gold that was in the initial alloy. And the same test in the same condition with the flakes gave us a number of results that range from 35% to the best case of 43–45% of recovery. That means that if you start with 85 grams of gold, you are recovering in the first pass only half of it with the traditional ways, while recovering 100% of it with the high feedstock refining technique. This obviously has a big impact for the refiners that are dealing with this type of alloy, and also push the boundary of the process of, for example, aqua regia to a higher silver content. With this type of feedstock, it will be easier to refine alloys with even more than 15%. 20%, or we still have to define the real boundary with the test that we are doing, but we expect that it will be much higher compared to the existing technology. So to draw some simple conclusion, we work on a very basic principle that is common to most of the chemical and electrochemical refining, which is that the fact that the actual reaction happens at the surface and the interface between solid and liquid. So having a big interface, a big surface, is a good advantage for this kind of processes. And we saw that the dissolution speed can be 6 to 8 times faster just by changing the feedstock shape. At the same time, the same positive effect is seen also in the range of alloy that we can treat in a single way through aquaregia with full recovery, even with 15% of silver in the initial alloy. And then we also compare this type of technology with other ways that we are familiar with to maximize the surface, and specifically the atomization process, in which we, again, by melting and by injecting high pressure water or high pressure gas into the liquid stream, we create a powder. Even with the atomization process, the result that we have with the high surface refining feedstock type is much higher in terms of speed and also capability to recover all the metal, without also avoiding all the issues that you have when you are dealing with fine powder of precious metal that are difficult to collect physically from the process because it goes everywhere. The next step that we will do is to repeat the same test on the electrolytic refining. It wasn't possible to present the result at this presentation, but we're very close to have a good set of data. And then proceed with the pilot plant, with an industrial type plant using this kind of process and technology. Before I conclude, I have to acknowledge and give my thanks to the Perth Mint refinery that helped us a lot with the testing phase, and also they gave us a great insight in the process and the parameters that are used by them and also applicable to this type of process. Thank you very much.